this one, normally I will repeat again the slides. Okay, so we have the actuator system, we have the measurement system, and the whole thing, the whole block over here will be the control system. Okay, and I'll just skip that. I'm going to go to the process. Okay, the front end and back end process. Okay, so student asks, just small. Okay, in semiconductor, can you see my screen? I'm writing semiconductor. We have the front end, and then we have the back end. Okay, so front end is where we have the wafer fabrication over here, and then for the back end is basically assembly or packaging. So wafer fabrication is that, what is wafer? So this is wafer. This is the end product at the front end. It's a wafer. So it's similar to what the wafer that you eat. Wafer, how do you see it? You have a wafer, something like this, a circle, and then you have some like square there, right? Wafer. So basically, on top of this wafer, there's a chip there, which is we don't call it a chip. Chip is something that at the end product of the back end, so we call it as the chip. But for the wafer is that on top of this, we call it as the die. Die, a small fabricated chip on top of the die. So what happened is that this wafer, okay, from the front end, okay, example, I take an example of Infineon. Infineon, we have two branch, which is we have the one in Kulim and the one in Melaka. Okay, so in Kulim is that we have the front end, and in Melaka is we have the back end. So basically, it's different product output over there. So in Kulim is that they actually come out with the wafer fabrication, and that wafer fabrication will be sent to Melaka to actually assembly it and become a chip. The chip that is being sent to the company, to other company, which is to the consumer. Example is consumer, like Honda, Proton. Okay, consumer, what type of chip are being sold to this consumer? Example are airbag chip. Okay, to the controller to control the airbag. So this is example of the chip being sold to the consumer from the Melaka back end. Okay, so for wafer fabrication process, if you see here, I'm going to open this slide. Okay, so there are many processes. Okay, the first one will be, I cannot write here. Okay, sorry, I cannot write here. So the first wafer fabrication will be the incoming wafer. First process, wafer coming in, and mostly that wafer coming in is from Germany, Infineon. Okay, so that wafer coming in, and then next process is epitaxy, diffusion. So all of these are processes, and each processes they have the machine over there. Okay, means that each processes have the engineer, have the technician, have the operator over there. Okay, so we have all of those processes until the probe and trim, and finally this will be sent out to the Melaka. Okay, and what I want to share is that the die bond processes. Okay, in the back end. So back end processes. Okay, if I were to show this slide, is on the, okay, we call the die bond processes is under the back end. Okay, assembly. Okay. So in Melaka is assembly processes. They do not come out with any wafer. They are actually assemble it to become a chip. Okay, so they have a chip pre-assembly. The wafer coming in, we have one chip. Okay, sorry, one wafer. So lots of wafer. Basically, they will send lots of wafer to this to the Melaka site, and then next process will be the laminator. Laminate first the top part, and next process will be back grind, mounting, and detaping. So back grind is that basically the wafer that being sent from Kulim to Melaka is a bit thick, and they're going to back grind the bottom part. Back grind it to be very thin. Okay, before they go to the sawing process. So sawing process is basically to it. We have the wafer, Okay, you know that the wafer have this lots of die on top of this wafer. Okay, example, this is the die. So they are going to cut the wafer at this line, cut it. Okay, so that we call it as sewing processes. Okay, next after pre-assembly, we have the front of line. This is where I mentioned we have front of line and end of line. End of line or end of line over here. So assembly process for front of line and the end of line have different environment, whereby the environment of dust. So they need to use different suit to enter the assembly line, front of line, or the end of line. Okay, different processes. So normally for the front of line, the engineers or the technician operator, they need to wear the full suit, the white suit. Basically from top to bottom, it's like a, if you have seen it, it's like in the video that I shared to you. So they were going wearing overall, full overall, even their head, and then wearing the glasses. Okay, so the first part of the front of line process will be the die bond. Okay, so what is die bond? Die bond process is basically after sewing. So after sewing, the chip will be cut into one piece like this separately, right? Okay, so you're going to actually bond it to the frame. Okay, there's a frame, so you're going to bond it to the frame. So later on, I think you can try to go through the video. Okay, this one is the video. Okay, so this is back grinding. Okay, laminating, wafer sewing. Okay, and then die bond means that they're going to pick the die, which is cut from that wafer, and then put it on the frame. Okay, die bond, and it's going to be cured using a glue. Okay, so these are the processes. Okay, and next after cured is next will be the wire bond processes. Okay, wire bond processes is basically like soldering, but using a very small distance a solder. Okay, it's very small in nanometer, so they're going to solder using machine automation. Okay, and next is QC gate to check the quality at the end of the front of line. Of course, for each of the processes also they have the quality check for each batch. And after that, all of this product is going to be sent to the end of line. And at the end of line is a bit robust. So they are going to go to the mold. This is where you see the chip that have the black mold, the plastic mold there. So this is basically mold and encapsulated on top of the chip there. Okay, and then post mold curing, dedamp and dejunk is basically to remove all the extra mold there on top of the processes. And next is marking. Marking is means that you know the chip sometimes if you know that it's come from Infineon, it's come from ST, you come it from the Texas Instrument. So there's the chop there. So that is what we call it as the laser marking, chop on top of the chip. And next is X-ray. X-ray is basically a form of QC check also. So they are going to do an X-ray top view, X-ray directly, and look at the connection wiring. So they can directly see if there is any wire overlapping or not connected to the point. So that is one thing. And they will also have the QC check using some instrumentation. So to check directly if the chip is good to be sent out. Okay. And lastly is the packaging and shipment. So that is basically the process at the front of line. Okay, and back end of line. So okay, some student mentioned about the process of ball screw. Ball screw. But I think I will just skip that first. Okay, because later on in chapter 6 we are going to go through. But anyway, you can just search in YouTube ball screw mechanism. So lots of video explaining about the ball screw mechanism. And I would suggest to student, other than, it's good that you mentioned that you don't understand this and that and so on. I would suggest, other than asking, if you still do not understand after looking through some YouTube or Google it, then you can ask the question. But if you still cannot understand, then it's okay. I will try to explain. Okay, so next. Ya, kejap. Tengah nak tengok slide.
Lag
Sorry.
dia.
Kejap. Mana chapter 1? Okay, chapter 1. Okay, in the slides, I think in the slide, basically my notes stop at 29, and then the recording stops. So, but basically you can just go through for each explanation. You can go through this diagram processes. Okay. Well, if I were to click that. Okay, so this is diagram processes. You see that there's a robot picking up all the die. This die is already being typed, saw processes. So it's going to be picking up die and put it on the frame. So you see that this is on the frame here. So this is the process of diagram process. Okay, and after that, of course, on top of this frame, they already put the glue, the glue on top of the frame. So they're going to pick it automatically. This is use automation. You have to put the diagram processes. Okay, so that is what plan to explain, recap on chapter 1. And you can also go through this mechanical job scope. Okay, I think you can just click on here, call for video job. Okay, and I just want to share, okay, example of Infineon job search. So you see it there. I'm not sure if it's working. This one was a long time ago, but anyway, let's just look at it. If accept. Okay, you can just see here. Okay, example. Just type their process engineer. Okay. You can see that, and then you can pick, because if you didn't have lots of branches, so you want to pick Malaysia. Okay, so you can see there is a few opening. Okay, senior engineer processes, wafer thinning. Okay, this is in Kulim. Senior wafer maintenance. Okay, maintenance process is different type of engineer. Okay, so processes is only on the processes. Maintenance is maintaining of the equipment. So senior engineer product engineering. So basically to design the product. Okay, this is basically on the R&D. Because you see that there's a Kulim there. So Kulim, they have the R&D over there. Okay, Malacca side, we don't have the R&D. They mostly on the assembly. So this is where you can just go through my slide later on to look at the link. Yes. So Okay, and then towards the end here is that I have example of mechanical system. Okay, so just go through example, nothing much, just go through there. If you don't understand what does it mean, then try to pick up the key point. Example, micro factory drilling unit, put it in YouTube, and you will find that explanation. CNC bending, what does it mean? Okay, CNC machine, what does it mean? Okay, and then you can look at all of the example. Okay, microtronic system. So why I share all of this, because all of the system basically they have all of the 3 block diagram. They have the sensor, okay, sensor, the measurement system. Basically they have the actuator system, and also they have the control system. So try to identify from this class, from this application, what type of sensor that is being used, what type of actuator being used, and what type of controller that you think it being used. Okay, so basically, if from the previous semester is after finishing everything, student need to actually come up with the group discussion, but this one no need. Okay, just look at the task, and if you have time, do it on your own. Okay, only on the sensor part. Okay, this is example vision, encoder, and pulse. Of course, we are going to go through other type of sensor. So what are sensor? Sensor is basically are defined as a device which is used to measure physical quality physical quality. Just look. Oh yeah. Okay, physical quality. For example, light, sound, temperature, okay, or force. You want to measure force, so you want to actually measure that. So it's basically measuring something. Example. Okay. Kejap, mana pergi? So example is that nowadays during the pandemic, what of sensor that you usually use? What do you think that you normally every day you use it? Can you share in the chat?
Thermosensor.
Yes, correct. So thermometer is actually sensor, kan? You go to the shop, you need to check.
Yeah, can.
So that is one type of sensor. Okay, but does it actually display anything? Yeah, it display the value, right? So you have a display unit also. So basically, the thermometer have two types of component inside it. They have the sensor to detect the measurement, and also they have the display unit, the LCD, basically. Okay, the 7 segment to display what is the reading, 36.7, 35.8, and so on. So those are type of sensor. But when we talk about mechatronic system, it's a sensor that actually can give feedback to us. Okay, so it means that the output can be collected and can be feedback to the reference to actually compare and get the error with the reference. Okay, so those are example of sensor. Okay, so patutlah you boleh jawab thermometer sebab dah ada so saya tak perasan. So that one is one example. Okay, but what is transducer? So transducer is actually similar to sensor. Okay, it can measure similar qualities to a sensor, but will convert the signal from one physical form to another, meaning their input and output signal are not the same. Okay, transducer are sometimes referred to energy converter. Okay, so a transducer will convert measurement into an electrical signal. So example is, okay, let's say that we take an example of input transducer takes the form of energy converted into electrical signal, and for output transducer is that it takes the electric and convert it to another form of energy. So example is that sensor is a light bulb. Okay, light bulb that detects motion. Okay, so basically you need to have a motion sensor. Okay, that motion sensor is connected to the light bulb. So detecting that, then it will actually lighten up another form of product output. Okay, so we call that as a converting. Okay, converting from electricity to motion. So that motion sensor is called a transducer. Okay, and that motion sensor is also a sensor because it can detect movement. Just that it's going to convert from electrical to motion. And when detecting motion, it's basically it's detecting the displacement. Okay, because motion is detecting the displacement. The jarak lah antara objek dengan sensor, right? So what are types of measurement system that we have? Basically, we have the motion. The common one is the motion type. Okay, force. Okay, temperature, pressure, flow. And you see that here is that when we talk about motion is that it doesn't mention displacement. So basically, when we talk about motion, it's detecting the displacement, jarak. So, and all of these are called sensor. Okay, these are physical quantities. So motion, force, temperature are physical quantities, and it can be detected using a sensor. And this sensor will normally need to have a signal conditioning. Means that it need to convert from electrical signal or from motion to a signal in terms of voltage or current. So this is where you need the signal conditioning. And lastly is that it's going to display it. For example, that thermometer just now is going to just display the reading. Or if you have a controller, then it's going to feedback it to a system. So the basic, I would say the basic concept of the system take one example is Tesla. Okay, anyone know about Tesla, the car, electric car? Anyone know about Tesla?
Yes. Yes, Doctor.
Mestilah kan. And you know, anyone know about X70? X70, not the S70. I just noticed that X70 ada phone juga Vivo phone X70. Okay, I saw it in the bulletin TV3, selalu TV3 dia ada Vivo X70. I was thinking kenapa lah dia iklan X70 Oh, rupanya there's a handphone, dia punya model dia X70. Okay, X70 sama dengan kereta So okay, maybe Proton tak buat copyright lah tu kan. So X70 So basically we see here last time when I was teaching the advanced manufacturing system for you student, I actually bring student to visit Proton COE Center of Excellence at Shah Alam. And this was back in 2019 before the COVID happened. And what actually brought them to look at the processes at the Proton COE, at the assembly processes. So we did look on the assembly processes. You see here you have the MVF, multi-vehicle factory at Proton. So I think there were roughly 2 buses. I bring student 2 bus, and actually I was lucky to actually get the slot because one of the manager over there was my friend from my school last time at St. Justine. So he was one of the manager over there. So he actually so he was one of the person who explained about the visit. And also actually if you see here, all of students looking at this person explaining about this engine, right? So this person, this is an engineer, actually is my brother, my older brother. He's a manager at the research department on engine, in production for engine, designing engine for Proton lah. One of the engine that they developed was for the X50 also. The current one X50 also engine by Proton. So he's one of the person in charge lah. Okay, so I didn't want to share that. I wanted to share about the video on this one. So one example of mechatronic system that you can see in a car is on example is Tesla. Another one that is locally is X70 lah. If you have X70 at home, then you know all of this. So basically, if you see here is that Tesla is actually 100% electrical vehicle. Okay, and it's autopilot. And if you see here, I think the link, maybe the link is not there. Okay, but the link later on I will show to you. Okay, just look at this video. Okay, so if you see this video, it's inside Tesla. Okay, the person is not actually holding the steering at all. So it automated. And you see that on the left side here, right side here, is that you have the left rear vehicle camera. Okay, left, you have the medium range camera. And then you have the, I think this is right vehicle camera. Okay, so they are using the camera to detect obstacle. Okay, you see the obstacle, the green, blue, and so on. So I think the blue is to detect the human code. And then they also detect the line. So basically, Tesla can actually do line following because not line following. It's actually to detect, to ensure that the car is inside the lane. Okay, so this is all using, like your friend said, is using AI and it's adaptive control. It adapt to environment. It does not only have AI, it actually adaptable to environment. Okay, so later, I think this one you can just look it, try to search. I give you the link. You can just save that link. Okay, or I can just share it in Bakelite later on. Okay, just close that. Okay, so one of the common thing is on the Tesla or even X70, they have that also. X70, mostly they have the They call it, currently they call it as the ACC, Adaptive Cruise Control. Last time when we have the Inspira, because I used Inspira. So Inspira, they have the cruise control. Cruise control, basically you can set the car to actually cruise at certain speed. So you want to set the speed at 120 km per hour, example, to avoid any summon kan. So you set the speed 120 km per hour at the highway, and the car is basically going to drive automatically, but the steering you need to still hold it okay, to maintain the distance. Okay, but in X70 is that they have the upgraded one, which is the adaptive cruise control. So when we talk about adaptive cruise control, is that it adapts to the distance with the front car. So previously, when we have the cruise control only, when our car is near to the front car, it is not going to stop. Okay, so it's just going to speed out and crash into that next car. That is what it means by cruise control. So you just control the speed, okay, without having any sensor to detect any obstacle in front of you or back at the back. Okay, but when we have in X70, they have the adaptive cruise control. So basically, they have all of the sensor. They have lots of sensor. I think basically they have the ultrasonic sensor. Overall, around the car, basically I think 8 sensors kot. Depan ada 3, tepi, belakang ada lots of sensor. So that sensor is going to detect the distance with the front car. Okay, so when it detect the car in front, the car X70 will directly start to slow down, braking. Okay, without the human braking. Okay, so this is what we call as adaptive cruise control. And after that, if the car in front already go to the right, okay, so the car directly automatically speed again to the reference that we set. So this is what we call as adaptive cruise control. A very simple idea on mechatronic system that has been applied to a real environment. Okay, so let's look at this example. So okay, so we look at this example. Okay, I think you have seen it when you are doing diploma. For the student who did diploma already, so you have seen this block diagram. And mostly when you look at a block diagram, this main block will be called as the block diagram of the system. So I'm going to draw that. So basically, you have something like this. You have we call this the block diagram with the system, complete with the controller inside. Okay, and when you have you want to control a certain reference, then you need to have a feedback loop. So feedback loop means that basically you are going to calculate what is the error between the reference with the output. Okay, so you will see that most of the time, you don't see this type of block. You actually seen this block. So if you see here, actuator system is normally connected to a measurement system. Okay, let me just take an example of a DC motor. Okay, if you buy a DC motor at the shop, DC motor, a very small DC motor, okay, DC motor do not have any sensor. Okay, unless you buy a DC motor with encoder. So there is an encoder connected to the DC motor. If there is no sensor, means that the DC motor, when you give an input, you give a voltage, what happens that it's going to actually rotate with the same speed. Okay, you cannot control the speed unless you control the input voltage. Okay, you want to give it 5 volt or 10 volt. So the more higher the voltage, the more higher the speed. So that is how you control if it's an open loop. Okay, that is example of an open loop. Okay, but nowadays they sell a DC motor with encoder. You can type like DC motor with encoder directly. They have the encoder attached to the DC motor. So that is whereby we have, normally you will see that something like this. The actuator system is combined with the measurement system. They have the sensor together. So when you have this type of block, then the output is look like this. Okay, same thing. It's the same thing. So if you remember signal flow graph in control block diagram last time, you can actually bring this block above here. So that's why it can end up looking like this. Okay, Okay, so in the measurement system later on, you're going to look at this part later. Okay, so chapter 2 will be on sense and transducer. Signal conditioning will be chapter 3 and data presentation will be chapter 4. So basically, it will be covering 3 different chapters. Yeah, I'm going to skip that. This one I already explained just now. So about the signal condition element, okay, the data presentation, what it is, okay, display data, graph, indicator, okay. So I'm going to skip that. You can just go through. Just directly go to the sensor performance characteristic okay, on the types of characteristic because it will be the SSS number 1. So for this sensor characteristic is that basically when you purchase a sensor, okay, before you purchase a sensor, you want to actually check what is the data sheet. What are the input? Is it voltage? Is it current that is required for that sensor? And then what are the output range? Is it the range of the, for example, if you plan to buy a display sensor, can it detect up to 50 centimeter? Or does it can only detect up to 1 cm, 1 centimeter? So you need to check that data sheet, the performance. So I'm sure you have seen a data sheet before. And what you want to look at a data sheet is that on the static and dynamic characteristic. So on static and characteristic are the value given when the steady state condition occur, which is after sensor have settled down after receiving inputs. Okay, so basically this type of static characteristic are in the data sheet. Okay, you can directly look at, what are the span value, what are the range value, what are the accuracy, what are the input, what are the gain. Okay, all are in the data sheet. And dynamic characteristic is the behavior of the sensor in transient conditions. So basically, when you want to check the dynamic characteristic is that you need to actually test it. Okay, test it in real life. Okay, you give an input, you collect the output and plot in a graph and to see the behavior in transient condition. So there are 11 types of static characteristic that can be referred to in a data sheet. Normally, you want to check if there is a range and span. You want to check what is the error reading. You want to check what is the accuracy, sensitivity, hysteresis, if there is any hysteresis value, non-linearity, okay, repeatility or reproducibility, okay, stability, deadband, resolution, and output impedance. So if you look at the first one, range and span is basically, if you look here, okay, the range is of a transducer is limit between the input that it can vary. Okay, and the span is the maximum value that the input minus the minimum value. So basically minus maximum minus the minimum. Okay, so if we take an example for a load cell. So load cell is a type of force sensor. Okay, to measure a force that have a range of 0 to 50 kilometer. Therefore, the span is 50 kilonewton. Okay, so these are example. And if we take another example of thermocouple, okay, so we can say that the input range of the thermocouple is from 100 to 200 degrees Celsius. Okay, and the output range is 4 to 20 milliampere. Okay, output range means that the reading, normally from a sensor, the reading should be in either voltage or current. The reading means that the reading taps directly from the sensor. The reading will not be the reading in Celsius. Okay, this is the gain lah. Basically, you can actually look here is the gain. Basically, if I were to write here, okay, this one, okay, they say the range is 4 to 20 milliampere. Okay, and it says here the range of the input is 100 to 200 degree. So basically, if you have 100 degrees Celsius, then it's going to give you a reading of 4 milliampere. If you have the value of 250 degree, then it's going to give you a 220 milliampere. So that's what it means by this one. Example of input range. And the span value is, what was it? is the variation between the maximum minus the minimum. So you have the 250 minus 100. This one. So you get the variation is 150 degree, and the span of the range of in milliampere is 60 milliamp. So this is example. So later on, you will refer to the example D5. D5 is what? Okay, D5 is you need to look at the ULearn, the datasheet that I upload in ULearn. So basically, in ULearn, go to week 2. Week 2. Okay, beside the notes chapter 2, there's a sensor datasheet there. Okay, and there I have uploaded 6 datasheet. Okay, datasheet number 1 is Dacel. Dacel is the post-war sensor. Honeywell torque sensor. Second one is torque sensor. Kiowa is what sensor? I'm not sure. Just check it. And then load sensor, load cell, and then we have the infrared sensor and Dacel. Okay, so different type of sensor. Okay. And you see here that the first sensor is Dacel TRB and Dacel TRC. This different model. Okay, different model means that different range and different span value. So later, what you're going to do in the breakout session is that you're going to go through the content, okay, of each of the datasheet according to group. Okay, that one is the first one, range and span. Second one is error. So the error is the difference between measured and the true value of quantity being measured. So basically, this one error when we have a block diagram lah, closed loop diagram. You have the closed loop. You have a block diagram here. If you have a block diagram like this is an open loop. And you know that when we want to make it into a closed loop, then you have a feedback form, plus and minus over here. So error is at this point. Error is minus here. So it's basically measured value. This is measured value minus the true value. So true value is over here. So error minus true value, you get the error value. Okay. So if you have something like this, actual value is 26 and measured value at this end is 25, then you have an error of minus 1 degree. Exercise. Draw the closed loop block diagram and label each parameter. I already draw it for you. Okay, sorry for that. But you can draw it on your own in the notes. Third one will be on the accuracy. Okay, so what is accuracy? So it's defined as the largest expected error between actual and ideal output signal. Okay. Sometimes this is quoted as a fraction of full-scale output. For example, a thermometer might be guaranteed accurate to 5% of full-scale output. Okay, so meaning that, okay, let's say we take a temperature sensor. It says that the accuracy is plus minus 2 degrees. So temperature sensor, if you buy a temperature sensor, it says that it can detect measurement up to, example, 100 degree. Okay. But in the datasheet, it mentioned that the accuracy is plus minus 2 degree. Means that it will give you either 102 degree or 98 degree, depending on that sensor that you purchase. Okay, because you know, when doing the manufacturing processes, assembly, there are some sensor, you cannot have the same value. Okay, unless it's simulation, then you can have a Z value 100 degree. But when you assemble, you produce it, some of the accuracy, when they do the testing, the accuracy of the equipment or the sensor, it will go up to plus minus 2 degrees. So that is what it means lah. So it means that it can go up to 102 degree or 98 degree. So they mention it also in the datasheet. Okay. Okay. Alright. Next is the sensitivity. Okay, sensitivity here is defined as the term of the relationship between input physical system and output electrical system. Okay, so basically, I already explained the sensitivity just now, but maybe you didn't get that idea. Is this part? Okay, sensitivity means that you know that the current or voltage value will give you a value of the output in terms of temperature. Okay, so sensitive means that actually is the calculation of gain. Okay, you see here the ratio between a small changes in electrical signal, small changes in physical signal. Okay, so that's why you see here the typical unit for sensitivity might be in voltage over Kelvin or voltage over degree. Okay. Or, for example, if you have a displacement sensor, then you have a voltage over millimeter, okay, in displacement. Or sometimes you have a voltage over centimeter. Okay, so sensitivity of the reading. And how to calculate that? It's very simple lah. Gain kan? Dia sebenarnya gain. So you have the output minus the input, then you have the sensitivity value. So you get the gain value. Okay, try to do this. Okay, hysteresis. Next, we go to hysteresis. So hysteresis is that, it's mentioned here is that some sensors do not return the same value output when the input stream is cycled up and down. Okay, the width of the expected error in terms of measured quantity is defined as hysteresis. So mean that, okay, example, you have a temperature sensor just now. Is it temperature? For example, this one is resistant with the flow rate. Okay, we have a sensor over here. So they are going to give a rise, volatility rise here. So it's going to rise like this. Rise up until this value, flow rate at 25 milli per second. And then after that, they reduce it. So the voltage actually drop, but with a different route. Okay, when a different route between this rise and drop, then we call this as hysteresis. So this is the hysteresis between the rising and the drop value, decreasing value. So this sometimes the sensor have this type of hysteresis. Not all sensor. So this one normally they will also mention it in the datasheet. Okay, next will be on the non-linearity. Okay, non-linearity sensor, I don't think it's common. Normally, all of the sensor are linear sensor. So, what does it mean by non-linearity is that this one. We have a linear sensor reading, straight line. And you have a non-linearity sensor. So, it's going to give you the same reading at the end here. But you see here, there is a gap. There is a slight difference when you start to give a value. Okay, so increasing value, that is not the same with this linear value. So this is what it means by non-linear. Sometimes it gives you a non-linear like this, okay, and something like this. It is not actually the same set point at the end. So there's a cross at this point. Okay, so this is something that you need to take note, because sometimes students just buy sensor without taking note on the data sheet. So they will just test it out and then they find out that, why does my reading does not the same as if I test the sensor on its own. But when you connect to a actuator, the reading is different. So you need to troubleshoot the sensor. I would suggest normally for my students when I do the final year project is that they purchase a sensor. They need to test the sensor on its own. Give an input to the sensor according to the datasheet. So if the datasheet says that the voltage or the maximum voltage to the sensor is 10 volt. So they test it from 0 to 10 volt. So 0 and then capture the data. 1 volt capture the data. 2 volt capture data, and so on. So when they have all those plotting data, they are going to plot it into a graph. So later, okay, in a data sheet, you will find out that they will normally give you a graph like this. And then after testing, the student already testing it in real life. So they have the data and they're going to actually compare it with the data sheet. So if it's the same, then means that the sensor that it's purchased is good. Okay, sometimes there is a bit off, so you need to take note on that. Okay, next is on the repeatability. Okay, repeatability is ability to reproduce the output signal exactly when the same measured input is applied under the same environment. Okay, so it means that you're going to actually repeat again. Repeat and repeat means that repeat 1,000 times. Is it going to give you the same value? Okay, so this is what it means by repeatability. Normally, when you are doing an experiment in a final year project, most of the time we will ask students to check repeatability at least 3 times, at least. But for my case is that normally I ask for FIP student is 5 times. For master student, 20 20 times repeatability of the same experiment to check that it's actually repeatable. Okay, lastly is the second last will be the stability. Okay, able to give the same output when measured a constant period of time. So stability and repeatability is almost the same, but stability is when you give an input to the system, okay, and then you just run it for like 8 hours. So is the data stable? Is it going to give you the increment data or going down? Okay, so when you do this type of stability testing, you need to have another sensor to as a reference. So that's where you can actually manage to compare the data. Next one will be deadband. Okay, deadband is where the sensor doesn't detect any signal. So you might find out that at certain value, there is no value. Okay, so it should be like this. Supposedly, your data, the sensor can detect range like this, but at a certain distance, it doesn't detect any voltage. So this is where we call it as the sensor has a deadband. Okay. Okay, lastly, is on the resolution. So the resolution is the smallest increment in the measured value that can be detected. So resolution is actually about the similar with the gain just now, the sensitivity. But when we talk about resolution is the smallest that it can detect value. So for example, if you have a temperature sensor, 100 degree detected. So if you have a very good resolution sensor, okay, a good sensor with high resolution, then it can go up to 0.01 degree. Sometimes it can go up to milli degree. Okay, so of course, when you have highest resolution sensor, means that it will be much more expensive. Okay, in the table, write it out like this, and then definition, figure, example from the datasheet lah. Okay, so and then I have given some example how to actually list it out and so on. Okay, so this is one of example. Okay, next we are going to go to the this one static dah. Okay, dynamic tu I think you baca sendiri je, tak nothing much. Okay, now I'm going to go to the selection of sensor. Okay, selection of sensor. Okay.
Betul nak tanya jap.
Ya.
Untuk yang exercise 2, 3 pun still group yang sama ke macam mana?
Yes, group yang sama. Group sama.
Oh.
So
Okay.
sebab tu tadi saya ada shoot dalam breakout session kan. Make sure dah ambil siap-siap lah nama group. Dah ada ambil nama group. Siapa tu? Alah, paling senang. Patutnya you guys screenshot je nama tadi kan dalam breakout session tu. So senang. Tak sempat nak ambil. Nampak nama boleh Chris letak kan. Okay, so the same group lah.
Okay.
For today is the same group. Okay, so next, because the topic is on sensor kan. So basically what you're going to learn is you have a system later on, and then what type of sensor is suitable. Okay, so you want to actually select the sensor based on size, okay, range and span to be measured, the type. For example, if the mechanism is a rotary actuator or is a linear actuator, so what type of sensor is suitable? Or do you need any mechanism inside there to actually convert from the translation between rotary and linear? So this is where in chapter 6, you'll learn more on if you have a sensor that can only detect linear motion. So how do you actually measure a rotary type system? Okay, so you can actually add on some mechanism in between so that you can actually measure those output. Next is the resolution. So higher resolution, as mentioned, will eliminate most of the error, because that error is that actually resolution means that you can detect very small displacement. Accuracy. So the accuracy is the difference between measure and true value. So accuracy is the plus minus just now kan, plus minus 2 degree. Okay, you want to have the accuracy is much smaller. Plus minus 0.1 degree is much more better than plus minus 2 degree. Because you want to have a exact value if possible. What are the material of measured object? Example, if the aim of the application is to detect obstacle. Okay, for example, the obstacle, imagine that you are near a sliding door. Okay, sliding door. And then there's an obstacle and there's something behind the sliding door. Okay, but the sliding door is made of glass. So what type of sensor is suitable to detect that obstacle? Okay, because if you were to take a type of IR sensor, infrared sensor, it cannot detect the sliding door, the material, the glass. Okay, so it's not suitable, even though it can detect this displacement, distance, or obstacle. So it's not suitable. Okay, so maybe you want to select ultrasonic sensor because it detect based on the frequency. So when it actually detect, they will send out a signal waveform in terms of frequency, and when it actually reverse back and it detect the distance, so that is where it can detect the displacement or motion or object. And lastly, which is normally we are constrained by the budget. Okay, and especially when you're doing final year project, so constraint, of course, you want to have a very good resolution sensor. Okay, so high accuracy, but the costing is really important. So you might have limited budget, so you need to make do with whatever that we have, with the best selection of the characteristic of sensor. Okay, so those are example. And most of the time, some of the sensor, they have their own amplifier with the sensor when you purchase. So example, it has the amplifier inside here. Okay, this is the type of amplifier that we have in the lab, in my lab, research lab. So we have this is a force sensor, and we have also, this is phone sensor, torque sensor, and it's connected to the amplifier box. Okay. So let's look at example of a rotary electromagnetic actuator here, mechanism setup. Okay, so which one do you think is the actuator and which one is the sensor? Is it A or is it B? Which one?
Actuator.
A or B?
A.
A actuator, sensor?
Sensor is B.
Sensor is B. Okay, so that's correct. Very good. So if I were to, let me just find the video. Where's the video? Electrical actuator. Okay, this video. Mana video dia? Yeah. Nampak tak actuator? Okay, this is the actuator showing the top view. Okay, the actuator, because this is made from electromagnetic actuator, so you see this coil there. This one is displacement. At the same time, we have the encoder at the back there. Okay, so those example of the actuator, maybe that one not too clear. Another example. Okay, this one is a linear actuator. So you see that the whole thing is an actuator. The sensor is over here. Nampak tak yang biru ni, yang warna hijau ni yang menyala? This one is the sensor. It's actually, if I play that again, it's detecting the displacement. Okay, so this mechanism at the hand here, we call it as a table. It's connected to the shaft, electromagnetic shaft here, inside here, so it will detect the motion. So basically, this one was built by my master student. Okay, a master student. Previously, he was my final year project student, and he did his master, and he graduated with master 2 years ago. Okay, so this one is example. So in this setup, you see that actually a similar setup. We have the amplifier over there. Okay, the input to the system, the actuator, and we have a DSP board, and we have the power supply, which is this amplifier. And we are using the rotary encoder to detect the rotation. So in this another example, I couldn't find the video, but later if I find it, I share to you. This will actually detect the rotation of the actuator. This is a rotary actuator in compared to that one just now was a linear type actuator. Both are designed by my student lah. Okay. And okay, just go to very fast. So let's see. Okay, let's say that you're going to measure a rotation. Okay, rotation of the actuator. You want, because in the end you want to control the displacement. You want to control it if displacement 0.1 degree, 0.2 degree displacement. So you might be thinking, where do you actually use this type of small displacement? Okay, remember just now the process that I showed to you in the semiconductor system, manufacturing system, the die bond processes, the wire bond processes. It requires very small displacement in nanometer or in millimeter, very small. So this is where you need to have this type of control. Control very small in micrometer displacement, or we call it as precision. Okay, motion. So my field is on precision motion, designing controller and designing actuator, very small scale one. So for this type of application, so you want to have the size of the range. Of course, for a rotation, you need to have a 360 degree. The type that you need are rotary type actuator. Of course, if you don't have a rotary, because rotary sensor might be very expensive, so you want to purchase only a linear type. So you can also use a linear type sensor, but you need to convert from the rotary to linear type. Okay, means that there will be a mechanism in between the actuator and sensor. The resolution, I want the resolution to have at least 0.1 degree resolution. Accuracy 98%, means that plus minus 2%. Material is ferromagnet, means that the measured object is ferromagnet. And the cost within budget. For example, I have a grant, okay, research grant. So it's within my budget, so I can purchase it. So this one is another task, which is a deadline is by Friday. Okay, and this is you need to submit to Yulen. Okay, the one that I showed to Yulen just now. So in a group, okay, by referring slide 59 to 88. So basically, okay, what you need to do is that refer to that slide. Student also may refer to textbook or other reference online available at the library. Okay, following the measurement sensor, fill in this template. So displacement, position sensor, okay, proximity sensor, velocity motion sensor, force sensor, until light sensor. Okay, based on all of these, for example, for displacement sensor, list 2 example for each input devices and explain its working principle by using a diagram. Okay, so in a group, you need to delegate tasks. I hope that when you have a group member need to have a team leader. Ketua siapa? That team leader needs to delegate tasks accordingly. Okay, so everybody need to do the task. Okay, tak boleh ada silent, panggil silent partner lah. Silent partner ni kita tendang keluar je. Kalau dia tak nak kerja, tendang keluar, tak payah nama dalam. Okay, so saya memang kejam sebab kita nak as a team work together. So give example of output devices actuators. So based on this displacement, so give also an example of actuator that can be used with this displacement sensor that you suggest. Okay, so for example, for the measured quantity is position. Okay, yang ni lah position, measured quantity position. Okay, so what are the input sensor picture? So I choose 2 because in here you 2 example. So 2 category of sensor under this position measured the quantity. So I choose incremental encoder, another one is potentiometer. So output devices, where can it be connected? To motor. So potentiometer, where can it be connected? Okay, theory of the principle and diagram of the principle. Okay, so this is where you need to search from references. So you need to do for each of the measured quantity. This is measured quantity. For example, velocity sensor, find 2 different types of category of sensor. Okay. So a lot lah ni. Kalau macam ni 9 2, 18. So 18 divide lah by 5 students. So mana dapatlah berapa kan. So divide the task accordingly. And another exercise 3 is also the same thing, group. Okay, so basically based on the group just now, okay, breakout session 1 to breakout session 9 tadi, okay, Refer to the a list of mechatronic project in Wakelet. So I have shared in Wakelet. Okay, Wakelet is, we have all of this. Ada 10. I already upload 10. Okay, so this example, maybe you will get different topic from the chapter 1 just now because of the switching of the breakout session. Okay, so based on that, what you need to do is, this is example. Okay, example of one of the example in final project was on the design and review of mobile robot for inter-office document. So the objective was to avoid obstacle avoidance. Okay, so maybe from the obstacle avoidance, you are thinking, oh, okay, there are 2 different types of sensor can be used. You can use a position sensor or proximity sensor. For line following, you might want to use light sensor, or you can use other types of sensor. You can suggest at least 2 different types of sensor based, I think, is it 2? Yeah, 2 types of sensor. So at least 2. Okay, so based on that, okay, this is one example. Just go through. This one is one example of one case study. So what you need to do is that, based on each of your projects, okay, case study lah. So if you get a case study on the rehabilitation for exoskeleton, so select the best sensor for the task and explain the reason why the sensor was selected based on measurement system. So in the video, they might not mention what was the objective of the project. So you need to think, oh, okay, this project was doing this one and this one to actually actuate the lower limb, so that to, and so on and so on. So based on that, in the video, they might explain what type of sensor is being used. Okay, what type of mechanism being used. So you need to identify it on your own. If it's not in the video, then try to search it using YouTube or Google. Okay, think of it as a task that you need to solve. Okay, how many sensors you think that is required? If you think there is more than 1 sensor required for that task, so you list it out. Okay, but based on the video, case study video, if it say that maybe you think there is 2 side sensor because you need to detect the position. So one is at the top position and one is at the lower position. So you need to have 2 sensor. So based on that, the third one is that assign the base location to mount the sensor and explain your reason. Okay, draw the front view, side view, top view. No need to draw using CAD lah, sketch je. Okay, so this one submit to Padlet. Okay, upload it, and I would suggest for this exercise number 3, exercise number 2, you can use Word if you want. Okay, and exercise number 3, submit it in PowerPoint slide. Means that for the first one, maybe one slide, second slide, third slide. So at least 3 slides for this task, and upload to PDF, and convert it to PDF and upload to to Padlet. Okay, so the deadline for exercise 2 and 3